In this chapter, we're going to be dealing with centripetal force and gravitation. Okay, first of all, centripetal force. Now, this applies to an object that's moving in a circular path, usually at constant speed. Now, even if it's moving at constant speed, the direction of the object is continually changing. Therefore, it's accelerating. Therefore, according to Newton's second law, this requires a force. The force is generally called the centripetal force. Centripetal force actually means directed toward the center that the object is moving, the center of the path. The centripetal force can arise from anywhere. It can be from gravitation, for example, can be an electromagnetic force, many different possible sources. We'll see in the next slide. Friction can also provide centripetal force. Okay, an example is a ball attached to a rope being swung in a circle. The person who is doing the swinging is applying this centripetal force. By the way, if the rope breaks, the ball is going to move on a straight path, tangent to the point where the rope broke. It's not going to move outward. The formula for computing centripetal force is mv squared over r. So the formula says that the centripetal force is directly related to the mass of the object. That's not surprising. Also directly proportional to the speed of the object. In other words, the faster the object is going, the greater the centripetal force needed to keep it in that circular path. It's inversely related to r, which is the radius of the path. So a small value of r corresponds to a very sharp curve. All right, now let's use this formula for centripetal force and see how it relates to automobiles rounding a curve. Now, first of all, if the car is going around a curve, it's going to need centripetal force in order to make it go in that circular path. And what provides that centripetal force is road friction. So one of the first things you can see is that if it's icy, then road friction is obviously a lot less, and that means there is less centripetal force here keeping the car on the road when it's trying to make that turn. And as you know, when you're faced with that situation, one of the things you generally do is reduce the speed. Because if you reduce the speed, then that means that you need less centripetal force in order to keep the car on the road. And since it's icy, there's not as much as there would normally be. The other thing is that when there's a sharp curve, in other words, when r is small, again, that requires a larger centripetal force, and one way that you can counteract that is to slow down, decrease the velocity to offset the increase in force needed because of the sharp turn. Okay, now we're going to turn to something that's called centrifugal force, and this one is a little tricky because centrifugal force is really not a force at all, but it's the effect of inertia. Okay, let's give an example here. Let's say that you're a passenger in the car and you're sitting in the passenger seat close to the door that's locked, hopefully, and you go around the sharp curve. Well, as you go around the sharp curve, you think you feel a force that's tending to push you against the side of the car door. Well, in reality, what's happening here is because of inertia, your body tends to want to move in a straight line, and as that car makes the turn, it feels as though there is a force on you pushing you to the outside of the car. All right, there's more details about this in the textbook, but one of the ones that your textbook shows is this example of ladybugs in a hollow tire, and how that if that tire is spinning, they tend to feel this centrifugal force on their feet due to the rotation of the tire. Now that same principle can be used to simulate gravity, because when astronauts travel in outer space where there's zero gravity, that does all kinds of bad things to the body. So if you can simulate gravity, you can prevent these things from happening. One way you can do that is to rotate the spacecraft. And as a result of this inertia or the centrifugal force, it feels as though your feet are pressed against the side or the bottom of the spacecraft. And this is the same effect that gravity has. Okay, now we're going to turn our attention to gravitation. Now, gravitation is the force that all objects that have mass exert on each other, which is essentially all objects, right? It's directly related to the masses of the objects and inversely related to the distance squared. We're going to talk more about this in the next slide. But the equation here is F is equal to big G m1 m2 divided by d squared. This big G is what's called the gravitational constant. It's a proportionality constant, and its actual value was not measured until 70 years after Newton died. The reason why it took so long is because it's a really small value. Take a look at this number, 6.67 times 10 to the negative 11. That's really small. And by the way, these are the units for the value of G. Okay, now because G is so small, it makes gravity a weak force. Actually, there's four fundamental forces in the universe, and gravity is by far the weakest. Really, it's only noticeable when at least one of the masses is large. So when you're talking about a planet, for example, then gravity is very noticeable. But if you take two objects and you put them side by side on a table, the gravitational force between those two objects is so small that it's certainly not noticeable, and it's extremely difficult to even measure it. Okay, now that d squared term in the denominator, we refer to that as the inverse square law, which means that the strength of the gravitational force decreases with the square of the distance. So, for example, if you double the distance between two objects, then the gravitational force between them is not halved, but it's quartered, because of the fact of that square term in the denominator. Okay, now, gravity is responsible for your weight. So, for example, your weight is really just the gravitational attraction between you and the Earth. But if you don't feel it, that condition is called weightlessness. So, as an example of this, this is the one I always used to give in class, that if you're at the top of the Empire State Building in an elevator, and all of a sudden the cable on the elevator broke, so you're plummeting down probably to your death. But in those last few seconds, you decide to do a little physics experiment. So you take a pen out of your pocket and you drop it. Well, does it drop? No. It floats right there in front of you because it is accelerating down at exactly the same rate that you are. So you and the pen and everything else inside that elevator, you're feeling this weightless condition. You're not feeling any force on the bottom of your feet. Okay, now, One of the interesting things about gravitation, other than the fact it's what keeps us on the Earth, is tides. And tides are a result of the gravitational attraction between the moon and the Earth. You might think it's the sun and the Earth, but the fact that the sun is very much more massive than the moon, but because of that inverse square law, the distance is so much greater that the moon has a much stronger effect of the tides than the sun does. However, when the sun does or can contribute some to the gravitational pull on the water, and these are known as spring tides and neap tides. They talk about this in more detail in your textbook with some diagrams that'll make it a bit clearer. But these are contributions from the sun, and it makes the tides either a little bit higher or a little bit lower than average.